Good morning, everyone. It looks like I set the wrong time on my YouTube video. Looks like I set it to 9:50. I thought I set it to 9:25. But anyway, we're going to get started right away. Hopefully that didn't confuse anybody because the links were up on Google Classroom and on Fax, RenWeb. All right, so let's get started. And we're going to go ahead and talk about a new topic today. I am drowning in all of the grading and other junk that I'm working on, so I'm sorry I have not finished grading, or I have not graded your quizzes yet, and I'm working on some other grading too. So if you're wondering about that, I am behind in that, so sorry about that. Anyway, so let's get started. Totally new topic today. Well, it's not totally new because we've talked about something similar, but it's not related to what we were doing previously on gases. So today's topic is going to be about redox chemistry related to energy and batteries and that kind of thing. And so here at the end, we're all going to be kind of looking at things having to do with energy, right? So we've just talked about global warming and energy. Now we're going to be talking about electricity production, so batteries and energy. And the next unit, we're going to be talking about nuclear, so nuclear and energy. So there's other aspects of nuclear. So nuclear is going to be we're going to spend a little bit more time on that. But really, for this whole topic of electricity, we're only going to spend 1 week on it. So that's it. And planning to have a quiz on Friday. So it's just going to be a quick couple lessons, learn some stuff on redox and electricity and batteries, and then just quiz, and then next week we're going to start something new. I think next Monday we have off, if I remember correctly. I think that's Memorial Day or something like that. So yeah, so I think we have no class next Monday. But time seems to be so relative these days that I don't even know what every day is. So anyway, I could be wrong. All right, so how many people? We got 4 people, so say hi to me in the chat. I see O'Brien's here. Everybody else, say hi to me. Let me know what's going on and that you're actually in existence still on this earth and all that kind of stuff. All right, Jonathan, good morning. Cool. All right. And Leo, awesome. Look at this. You know, we got 2 people online right now who are, wait, I don't even know. So Leo, are you in China right now? And O'Brien, where are you? I don't even know where you guys are. But anyway, awesome. If you're working especially hard, if you're coming here from China. Oh no, you're still here in America. Okay. All right. I thought maybe you had gone back. I don't know. A lot of students have gone back already, and there's no reason to even stay here because, right, we're definitely not going to reopen classes this spring anyway. So anyway, let's get started on the new stuff, and everybody else is going to wake up and join us later. You guys all should have one of these things. And I recommend printing it out. So I uploaded it 2 different places. One place is on just like the stream on Google Classroom, and the other place is on the assignment area in Google Classroom. So this is uploaded in 2 different places. Morning, Max. All right, and so I recommend printing it out. If you'd like to do everything digital, that's fine. It's just that it's annoying to go flipping back and forth. So if you have 2 digital devices, let's say a phone and an iPad or something like that, then that's fine. You can just have that as a reference on one of those devices, okay? Otherwise, I recommend just going old school and printing this out because this is going to be our reference for this particular unit. And obviously you're going to use it in the quiz that we're going to be having probably on Friday, all that kind of stuff. So print it out. This is a more sophisticated table of something you guys have seen before. You guys have seen a reactivity table, which is similar to this, but this is a lot more sophisticated because it has different, well, these are all just reduction reactions. We're going to talk about what in the world that means here in a second. And it has the voltage of all of these, okay? And so these are voltages. We're going to be calculating voltages of various different reactions, and we're going to need these voltages in order to do that, okay? And so here's our redox potential or standard reduction potential for various different chemical reactions, and that's what we have here. So this is going to be very important, this particular unit. and I believe I just took this table straight off of the AP chemistry tables and all that kind of stuff. So this is, I don't know, fairly official. All right, so let's get started here. We are going to kind of relate this to what we've done before in terms of redox reactions, and then we're going to expand upon our redox reactions and learn some more stuff. So let's get started. So we have solid magnesium metal is added to an aqueous solution of silver 1 nitrate, and I want to say right away that every reaction here that I'm going to have on this assignment is a reaction. I'm not going to throw in any no reactions here, okay? So just an FYI, if you're wondering, oh wait, does this reaction happen or not? Don't worry, all of these reactions that are in this homework assignment, they are reactions, okay? So we can remember, okay, well, what kind of reaction is this? Let's even think about it. We have a solid metal added to an aqueous solution. Well, any time that we have encountered a solid metal added to an aqueous solution, it has been a, anybody remember? Well, I'll let you guys think about what kind of reaction this is, but let's go ahead and write it out. So solid magnesium metal, that's going to be MgS. And then anybody have any guesses as to what kind of reaction this is? Just write it in the chat and I'll see if anybody gets it right. It's added to an aqueous solution of silver 1 nitrate. So silver is silver 1 is +1 and nitrate's -1. So it's AgNO3, just like that. This is aqueous and it's going to react. And let me see, do I even say what? No, I don't even say. Okay, so we have to kind of figure this out. So I'm going to help you guys out with this reaction and how we know what happens and all that kind of stuff. All right, but it is, well, yes, it's, okay, you guys are both right. It's redox and it's single replacement. Okay, so specifically, we learned this before as a single replacement, and we said all single replacements are also redox reactions, and we're going to be focusing on redox today and thinking about in more detail what is going on in a redox reaction and all that kind of stuff. Okay, so yes, because we know it's a single replacement reaction, we know that the magnesium is going to kick out the silver, right? And when magnesium kicks out silver, well, we recall before, so silver is a +1 charge, but magnesium is not. The charge of magnesium, anybody know? Magnesium is right there in the second column, so the charge of magnesium when it's an ion is what? Anyone remember? And there's only, I look, 6 people now, so there's only 6 of you, so I know it's not a lot of people to call from, but what should be the charge of magnesium when it's an ion? It's going to be a +2 charge, right? So magnesium in the second column is going to be +2 all the time, anytime it's in an ionic compound. Obviously, the charge here is 0, and the charge there is 2+. Okay, so it's going to go into magnesium 2+. And nitrate's still going to be, nitrate's always NO3-. So I'm just writing down the charges of these particular ions. So what happens is the magnesium comes, kicks out the silver, and you're left with just plain old, we'll do it this way, we'll write the silver first. Solid silver metal, so silver gets kicked out, plus you have magnesium nitrate. And magnesium nitrate, because magnesium's a 2+ and nitrate's a 1-, is going to be MgNO3 2. Okay? And this, of course, is going to be an aqueous solution. All right, so we have a solid added to an aqueous solution, making a solid in an aqueous solution. The magnesium comes in, kicks out the silver. You get silver as now your lonely guy, your single element, and then magnesium's in the compound. Okay, that's a redox reaction. And it's also a single replacement reaction. So what would you expect to observe? So if we recall, we've done this, I know it's been a while, but we've done this actually in the lab, and we're going to expect to see that some silver growing on the magnesium. Okay, and if you recall, it kind of looks a little bit, you know, dusty looking, this powdery stuff, and it's going to grow right on top of the magnesium surface. And that happens anytime you're doing a single replacement reaction. That metal is going to grow, this metal is going to grow right on this metal's surface. Okay? Until either all of this runs out or all of this runs out. Typically, your solution is going to run out first, but not necessarily. Okay. What is oxidized? What is reduced? Now we need to get into what we've done before and think about this whole oxidation and reduction thing. Now, if we recall, well, we need to even remember what in the world does oxidation, what in the world does reduction mean. So let's make sure we define those here. So the oxidized, remember that Leo, and Leo's with us this morning. This is awesome. So Leo says what? Leo's a lion, right? Leo the lion says grrr. Okay, so what does this mean? Losing electrons is oxidation, gaining electrons is reduction. So the thing that in this reaction is losing electrons, that thing is being oxidized. The thing that's gaining electrons is the thing that's being reduced. So we have to look at this and say, well, which thing is gaining electrons, which thing is losing electrons. And before we even do any of that, we should notice that nitrate, this nitrate right here, is NO3 minus here, and it's NO3 minus here. So nitrate is not changing. Okay? Nitrate is not being oxidized or reduced. So the only two things that are being oxidized or reduced are your magnesium and your silver. Okay? So in order to kind of see what's going on, we need to recognize the charges of all of these. Okay? In this case, magnesium has 0 charge. It's an element, 0 charge. Okay? And because it has 0 charge, or because it's an element, it has 0 charge. It's not positive, it's not negative, it's not an ionic compound. But silver in this case is in an ionic compound, right? It's silver 1, so it's a +1 charge, right? Over here, the charge of silver is 0 because it's an element. It has 0 charge. And over here, magnesium in a compound is a 2+ charge. Okay? So guys, let's just pause there and think about just, does this whole charge thing make sense? Make sure that makes sense before we go any further. So Leo is asking here, what is redox? So redox is, it stands for, and I'm going to run out of space on this particular problem. So let's just do it here. So redox is short for, so re stands for, or no, red stands for reduction, and ox stands for oxidation, because reduction and oxidation never occur on their own. In order for reduction to take place, oxidation also needs to take place. So a chemical reaction is neither, it cannot be only oxidation or only reduction. A chemical reaction would be an oxidation-reduction reaction, and we simplify that by just saying redox. A redox reaction is an oxidation-reduction reaction. Right? Oxidation meaning something is losing electrons and something is gaining electrons. Okay, so back over here. Are we all good with the charges? Okay, 0, +1, 0, +2. We should be all good with those charges. All right, so let's think about, what does those charges mean? That means that magnesium is going from a 0 charge to a 2+ charge. And in the process, magnesium must be losing 2 electrons. So if magnesium is losing 2 electrons, magnesium is being oxidized, right? Whichever thing is losing electrons is being oxidized. So magnesium is oxidized. Right? Silver here is going from +1 to 0, so it must be gaining electrons, right? The charge is going down, which means the charge is being reduced, which means it is gaining electrons. Okay? Remember, electrons are negatively charged, and so they're able to remove a positive charge. So silver, silver is being reduced in this case, okay? Because it's going from positive charge down to 0. So the charge is being reduced and the metal is gaining electrons, and so we call that reduction. Okay? So that's, let me see. So that's what's being, what other questions do we have here? Balance, what would you expect to observe? What kind of reaction is this? What is oxide? What, okay, so that's all the questions. The only thing is I think we haven't balanced this, right? So if we notice that we have over here, we have 2 nitrates, and over here we have 1 nitrate, and so we need to balance those nitrates. So I'm going to go ahead and put a 2 over here. Now that gives us 2 silvers, and so we need to put a 2 in front of the silver so that everything's now balanced. We have 2 silvers on both sides, 1 magnesium on both sides, and 2 nitrates on both sides, so the reaction is balanced. All right, let's pause there, and this is mostly review so far. We're going to jump into the new stuff in a second. Do you guys have any questions? Does that make sense? And these charges are going to be super important that we understand them before we move on. So make sure you understand the charges and that you understand what I'm talking about in terms of what's oxidized and what's reduced. So are we good? Crickets. Crickets. Are we good? Okay. So either we're good and you guys don't feel like saying anything, or we're not and you guys don't feel like saying anything. Anyway, I'm gonna just assume you guys are good because I don't see any comments going on. Maybe you guys' keyboards aren't working. Whatever. So for the above reaction, write out the full ionic equation. Identify the spectator ions. Now we have never done this before, so this is a new thing. Well, what is a full ionic equation? A full ionic equation is basically saying, all right, this reaction is occurring in aqueous solution. So a lot of these things are not together. Remember, we said when sodium chloride dissolves in water, it splits up into sodium ions and chloride ions. The two things are not together. So what we're going to do when we do a full ionic equation is to separate everything into what it actually is in solution. And what they are in solution is, if it's a compound that's aqueous, these two things are not necessarily together. In fact, they're probably not. They're swimming all around in solution as separate entities, separate or separated ions. So let's go ahead and represent that through what's known as a full ionic equation. And so we're going to start off with just MgS, and that doesn't change at all right? And then we're going to say plus 2Ag plus. Now, we technically, because it's an ionic equation, we technically don't need to write out that it's AQ because it's charged, we know it's AQ, but I'm going to go ahead and do it anyway. AQ plus, we have 2 nitrates, 2NO3 minus AQ. Okay, that's the reactant side. Okay, I can't split this up, so it's still S. All right, and if you have an S that is a compound, you don't split that up either. All right, we're only going to split up our aqueous solutions into the separate ions because they're two separate things when they're in solution. All right, and we have a 2 here that goes to the silver and to the nitrate. All right, then we have over here, we have 2AgS, right? That doesn't change, but this is aqueous, so it does change. And so this is going to be Mg2 plus AQ. And notice that we have a 2 here, so this means 2 nitrates. And we're going to put it out in front because it's not a part of a compound anymore. So this is 2NO3 minus AQ. That is important that you note. All right, it's not confusing, it's not strange. We have 2 here, which means we have 2 nitrates. And when it's written not a part of a compound, you must put the 2 in front, right? So we're going to put the 2 here in front of the nitrate here, okay? And it's going to look like this. So this is the full ionic equation. All we've done is taking our aqueous compounds and splitting them up into their 2 individual ions, all right, and they're both going to be aqueous. If you have any subscript here, you need to make sure that that comes in front here on that particular ion, Okay. All right. Good. So next, identify spectator ions. So this is a new term that you guys are learning here today. A spectator ion is kind of what it sounds like. All right. A spectator ion is an ion that doesn't do anything in the reaction. All right. So let's write it down here. So spectator ion, they don't do anything, they don't change or do anything in the reaction. They only watch. Just like spectators, right? Spectators for sport, right? You're watching the sport. You're not actually participating in the sport. You can cheer all you want, but you're not going to actually affect the outcome. That's what your spectator ions are. And how do we identify them? They are exactly the same before and after, although the number in front might be different if it's only some of it is a spectator ion. And we're not going to find any of that. That's going to be a more complex situation. You will find in every case that we do that the numbers are the same too. Okay? But a spectator ion is exactly the same on both sides. And that's important. Okay? So what do I mean? Well, if we look at magnesium here and we look at magnesium here, that is not a spectator ion because they're not exactly the same. Yes, that's magnesium, one magnesium. Yes, that's one magnesium. But look, that has 0 charge, that has 2+ charge. That's solid, that's aqueous. That has changed. So magnesium is not a spectator ion. Let's look at silver. Silver, there's 2 silver pluses here, and here is Ag. That has a plus charge, that has no charge. That's aqueous, that's solid. That has changed, so it's not a spectator ion, okay? It has to be exactly the same on both sides of the equation, all right? And even if they have the same, even one small difference makes it not a spectator ion. So let's suppose this was AQ and this was AQ. It would still not be a spectator ion because we have a positive charge there and no positive charge there. So very important that those are not spectator ions. The only spectator ions are, well, look at this. Nitrate, 2NO3 minus AQ. Over here, 2NO3 minus AQ. The charge has not changed. The state has not changed. The number has not changed. It is identical on both sides of the equation, which means the nitrate is not doing anything. The only thing the nitrate is there for is simply to balance out the charge of the silver. Okay? It's not participating in the reaction, it's only watching. And so it's exactly the same on both sides. So nitrate is the spectator ion. And typically, if you find any kind of polyatomic ions in these, typically those polyatomic ions are going to be your spectator ions. All right? But not necessarily. You do need to think about it a little bit just to make sure that that's the case. But typically, when you see polyatomic ions, they're going to be spectator ions. Also, things like chloride, bromide are often very often spectator ions. So, next, what is this net ionic equation? The net ionic equation basically says we're going to do this, write the same thing over without the spectator ions. Okay, so net ionic equation means what? Means no. So so erase spectator ions. All right, that's what a net ionic equation is. Okay, so net ionic equation means that we're going to erase all of our spectator ions, and that's going to be our reaction. Okay, so and this is very useful because it helps us to remove the baggage and kind of focus on what's actually happening. And so let's do that right now. So we have MgS plus 2Ag plus AQ. Not going to write that spectator ion. Goes to 2AgS plus Mg2 plus AQ. Okay, and that's your reaction. We're not going to write the spectator ions for either of those. Okay, so that's your net ionic equation, and it's important for two reasons. Well, actually three reasons. First of all, it's smaller and neater. Secondly, it helps us to focus on what's actually changing. And thirdly, you can recognize that this exact same reaction will happen if we change the nitrate to something else. Now, in this case, if we change it to chloride, well, all of a sudden silver chloride is not soluble. But if you change it to something else that is soluble, I don't know, silver, who knows, silver perchlorate or something, okay? You can change this spectator ion out and the reaction will work the same way, okay? Everything else about the reaction will be the same. So the spectator ions, it's not important what they are because you can just switch them out and trade them with some other spectator ion and the reaction works exactly the same way. Okay, so this is a net ionic equation. All right, last thing that we're going to do. Now, what we want to do is we want to split this net ionic equation into two different... Okay, are we back? All right, technical difficulties. It seems to be a daily occurrence, at least in one of my classes every single day. Anyway, so what we want to do now is we want to split this reaction into two different half reactions. All right, and so it might look a little bit strange, but let's go ahead and do that. We've already identified, okay, that magnesium is being oxidized and silver is being reduced. And so let's now write out exactly what that means. Let's start with magnesium and say, okay, magnesium is being oxidized. So it's going from Mg and turning into Mg2+. Okay? And when it does that, well, what happens? The magnesium, when it goes from magnesium 0 to magnesium 2+, it is losing 2 electrons. That's why it has this 2+ over here. And so we're going to write them down as plus 2E minus. All right? So it's losing 2 electrons in that process. Okay? And this, because it's losing 2 electrons, this is oxidation. All right? The other half reaction is, well, what's happening to silver? Well, silver is being reduced. So on this side, it's A, and I'm just going to divide by 2 because, well, I can't. If you write 2Ag and 2Ag, that's fine. But when you split into the half reactions, you don't need to. Okay? So Ag plus is turning into Ag, and this is Ag plus Aq, is turning into Ag solid. So what's happening? The silver, when it's going from +1 to 0, is gaining an electron. So I'm going to write plus E minus for electron over here because it's gaining 1 electron when it goes to silver 0. The silver is being reduced. Okay, so far so good. So these are two different half reactions. This is the oxidation half and this is the reduction half. The two half reactions cannot occur on their own. All right, they cannot occur on their own. You can't have magnesium being oxidized all by itself. If magnesium is oxidized, something else must be reduced. Okay, but we have effectively split them up to kind of just focus on what's going on here. When the magnesium is oxidized, it's losing electrons. When the silver is reduced, it's gaining electrons. And we call these two different half reactions, the oxidation half and the reduction half. Now what we're going to do now is we are going to look these half reactions up on this table right here. Okay, and I don't know if we can fit both of these pages in here. I'll try my best. All right, so we're gonna try to find both of these reactions on this table over here. Okay, and so you guys have these tables. Let's look at the first one, magnesium, and so we're gonna find, okay, magnesium, 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 magnesium. Okay, it's where is magnesium? It's all the way at the bottom here, and magnesium. I don't know. You guys can't even see it here. Okay, so now you can see it. So magnesium is all the way at the bottom. This is magnesium here and magnesium 2+ over here. Notice that the reaction that's written on here is the reverse of what you see here. Okay? And that's because you don't need to show both sides, because the reverse is just the, just the opposite of it. All of this, so if you notice at the top, this is called standard reduction potentials. All of these reactions are reduction. Now, all you need to do in order to find out, okay, what about the oxidation reaction? The oxidation reaction is simply this, whatever's here in reverse, okay? Just whatever's here in reverse, and that's the oxidation reaction, okay? So what we're going to do is we're going to find the magnesium one. All right, so it's Mg2 plus 2E minus goes to make Mg, and that has a voltage of negative 2.37. Okay, now here's important. Because we have reversed this reaction, our voltage is also reversed. What do I mean? So we're going from magnesium and turning that into Mg2 plus and 2E minus, and so that's going to be the oxidation, which means instead of our voltage being negative 2.37, our voltage is positive 2.37. So right over here, okay, so we can see, okay, this is the reaction, this is a voltage. Our voltage for this is going to be positive 2.37 volts, okay? Actually, it's not this. I should write a, technically speaking, this should be an E, okay, for the half reaction, okay? The electric potential is going to be positive 2.37 volts, okay, for that. Next, let's look at the second one, all right? And we'll continue talking about this voltage here in a second. Let's find the silver, all right, we want to find this reaction. So silver plus goes to silver 0. All right, can we find it on here? Look at this, it's way, way, way up here. So we have silver plus electron goes to silver metal. It's going to be 0.8. All right, so that's the voltage of this one. So silver, and notice we're doing the exact same thing. So the reaction that's happening in this problem is exactly the same as this reaction right here. Okay, and so our voltage in this case, our E, our electric potential, is positive 0.80 volts. Okay. Now what do we do with all this? Okay. Couple things to note. When something, for the oxidation ones, we flipped the reaction, and so the negative became positive there. Okay. And what else? When we do the reaction here, we're actually doing twice as many things here. Right, so it's actually twice as many. We have 2 silvers that are being reduced to make 2 silvers, right? So 2 silver plus to make 2 silver 0, right? But we do not multiply this number by 2. The voltage doesn't change. The number of electrons is affected, right? You're making 2 electrons and not 1, or you're using up 2 electrons and not 1, but the voltage doesn't change. The voltage just has to do with how much that reaction wants to happen, not the amount of that reaction happening. So we do not multiply this number by 2. Okay? That's very important to note. We do not multiply this number by 2. The voltage doesn't change. The only time the voltage changes is when we're turning it from negative to positive or positive to negative, simply because we flip the reaction. So if you flip the reaction, the voltage flips, but if you multiply the reaction by 2, it does not affect the voltage. Okay, I think I said that enough. All right, so what do we want to calculate the standard voltage of the reaction. So our total voltage, so we're just going to do it this way, E total is very, very, very simple. All you do is we just add those 2 things together, okay? No matter what. One of them might be positive and one negative, doesn't matter. Add the 2 numbers together, whatever they are. So if it's negative, you're adding a negative number, which means you're subtracting, okay? But you were just going to add those 2 voltages together. So the total voltage is going to be, and you don't always have to write a positive. In this case, I'm not, all right? So the total voltage is going to be 2.37 plus 0.8, and so that's going to be, what, 3.17 volts. That's it. That's your voltage for this particular reaction. And that voltage, a voltage is essentially like this it's known as electric potential, or kind of the driving force for an electrical or redox reaction to happen, okay? And so it's how much that reaction wants to happen. Anything that's positive, the reaction really, really wants to happen. If it's negative, the reaction will not happen, okay? The more positive this number is, the more it wants to happen, okay? And this is the same kind of voltage that you find for your batteries, okay? So you're talking about, let's say, a 1.5 volt battery. That 1.5 volts comes from a chemical reaction like this, okay? And if you were to use a magnesium silver battery, and you can do this, you can make a magnesium silver battery, your battery would have a voltage of around 3 volts, right? 3.17 volts, right? Depending on the certain amounts of chemicals you use and all that. Okay, so this is a voltage that is related to batteries. Now, next time we'll talk about voltaic cells and batteries and how they work. But let's first just focus on the chemical reactions and be able to do that. Okay, so any questions? For homework, you guys are going to have to do this for 3 different cases. So you have zinc and copper 1, okay? So same kind of idea, zinc and copper 1, which is, zinc and copper 1 is actually very, very similar to this. Very, very similar to that. And then we have one that's got a little tiny bit different, but very also quite similar. Aluminum and nickel 2 nitrate, okay? And then last of all, sodium and water. Now this last one is a little bit different from the other ones. So not sodium, potassium, sorry. So potassium and water. So this one's a little bit different. So solid potassium is added to water. It's a little bit different, but it's not so different. And so let me just give you guys a hint when you're wondering, okay, what's going to happen? Well, you already know what's going to happen to potassium, right? So potassium is going to be oxidized, and we already know, right, potassium is in the first column right here, so it's going to go to K+, okay? And so you can kind of guess, you can use this table. If you don't know exactly what's going to happen, you can kind of look it up on here and say, okay, well, what happens to potassium? So potassium, you find potassium way down, let me bring it up here, way down at the bottom here, okay? But this is not what happens because you're starting with potassium here. So it should be the opposite of this, right? So K going to K+ and E-. So that's what's happening to potassium. No big deal. We're kind of used to that. But what about water? That's the new kind of twist to this one. What happens to water? Well, we have to, and this is tricky because water is here and water is also up here. And you have to think about it and say, okay, do you want water as a reactant or do you want water as a product? And this is kind of the thought process. I'm not going to write anything down, but I'm going to kind of think through it. And so you guys can think about this last one as you do it, okay? If potassium, we know potassium starts out as this, and so it's going to this. So we know for potassium, we're flipping this reaction. So potassium is oxidized. If potassium is oxidized, water must be reduced, which means that we want to find the reaction here where water is reduced, which means we want to find the reaction here where water is a reactant and not a product. So this up here is not the reaction because water is a product, okay? And we don't want to flip it and have 2 things that we're oxidizing. We need to have one thing that's being oxidized, one thing that's being reduced. So we need to find water on the reactant side, and there's only one here. This is water on the reactant side, and so this is the half reaction for water, and this reverse of this is the half reaction for potassium. So that's about all I'm going to say. And so yeah, Leo, you're on the right, the right thing. So water is going to be reduced, so it's gaining 2 electrons, is going to hydrogen and hydroxide, and so that's what's going to happen when you add potassium to water. Okay. So I'll let you guys figure the rest of that out. That's going to be due tomorrow, and I think we're all done for today. Any questions? All right. Guys, make sure you spend some time and master this. If you can get this, if you get this homework all right, and you can figure this homework all right, the next one's going to be easy. Okay? But if you're stuck on this, the next one's going to be hard. So make sure that you spend some more time figuring this out, and then tomorrow when we talk about batteries, voltaic cells, it's going to be easy, okay? So Do all these. It's only 3 problems. Work through them, figure them out, go through all these different steps, and I will see you guys back tomorrow morning, same time, and that's it. All right. Any last minute questions before I sign out? All right. In that case, I'm just going to say bye, and I am out of here.